This one for all my peeps that pass. God bless they rest. And check it out. Now I'm paying cause it's mad real.
Yo, it's time for Carnegie Mellon University's Future Data Systems Seminar Series. This seminar is made possible by Google.
All right, guys, let's get started. We're excited today to have our friends at XTDB, James and Jeremy. They're calling in from the UK, and Jeremy has a 5-month-old at home, so we appreciate him taking the time out of that. Although the kid should be asleep right now, right? In theory.
Yes,
yeah. So again, we're super excited for them to join us all the way across the ocean. As always, if you have questions for James and Jeremy as they're talking, please feel free to unmute yourself and ask your question at a time. And that way they're not talking to themselves for an hour on Zoom. And again, James, Jeremy, thank you so much for being here. The floor is yours. Go for it.
Thank you, Andy, and thanks everyone for joining. So there's a lot to cover. I'm going to go as quickly as I can, but hopefully not too quickly. And yeah, please do interrupt. So there's a common saying that those who don't learn from history are doomed to repeat it. And nobody can be totally sure of the origin of the saying, but the quote is most accurately attributed to philosopher George Santayana, who in 1905 wrote, "Those who cannot remember the past are condemned to repeat it." So slightly different. Now, I think in an age rife with corruption and hallucinations and just poor decision-making in general, XTDB equips our users with the full might of SQL and relational theory to take on the challenges of remembering. So reconstructing history, it's actually a triple entendre. I want to talk to you about like why auditing is important, what it takes to actually be sort of auditable for a system to be auditable. But I also want to look at like why the industry is in its current state, because I think the lack of care for how we preserve history has sort of allowed the ecosystem databases to evolve into how they are seen currently. And finally, we want to, of course, look at how XT reconstructs history internally, so how we accelerate that and make that efficient. So James and I have been collaborating on XT for about 6 years, backed by a consulting firm called Juxt, which was founded by a pair of Lisp hackers who are writing Clojure in banks. A lot of that last 6 years was actually spent on version 1, which we're not going to talk about. This talk is all about version 2 of XT, because we needed to build a SQL API and we wanted object storage. And this year we released version 2 in conjunction with a few design partners. And this is a ground up rewrite specifically so that we can scale out an object storage and offer a SQL API and build it all in Apache Arrow. So lots of databases give you time travel and the ability to create snapshots. It's in the system time dimension that you're allowed to do consistent reads. So you can take a timestamp or a log sequence number and then generate a snapshot. Maybe you can do this retroactively. And you can use that snapshot to run and rerun queries. And this is useful, but it has limitations, and the operational mechanics of how that works can be very gnarly and difficult to predict and to cost. But this kind of time travel isn't necessarily that interesting. So the kind of time travel we're interested in is what was the state of the world rather than what was the state of the database. And so in the world of finance, you typically end up with loads and loads of timestamp data coming from all kinds of sources. And what you really need is auditability over everything that you do or that someone else using the system does with that data. You want to be able to reconstruct what that person knew at any given point in time. So the typical approach to solving this is just to keep loads and loads of data immutably. And you could be using many different databases or places, maybe it's data lakes and things, to keep snapshots, keep immutable data all nicely structured and organized. And then on top of that, you run reports, and then people make decisions based on those reports. And then further down the line, someone comes in and they want to audit those decisions. And in the background, you have all these machine learning people trying to figure out how to improve the processes going on in the organization. But this whole image or architecture can be split across many different systems, and it's chaotic and requires plumbing many things together. But what we really want to do is to solve this in a more unified, cohesive model, which is what's been has been going on since the 1980s. People have been researching this idea of the bitemporal model, been trying to apply it into databases. So Richard Snodgrass, who I don't know if he illustrated this diagram, I think it's a great diagram, very confusing though, so we won't do any more 3D diagrams after this. He showed that you can look at time using these two time dimensions and make things a lot simpler. And he actually wrote a book in 1999, published it. Jim Gray wrote the foreword for it. Jim Gray thought very highly of the book and its contents, so big thumbs up from that. So the bitemporal model, as Richard Snodgrass outlines, is a good thing. Let's assume that. And what it does is it's a model of change which accounts for errors and delays. So we'll dive into exactly what that means. But the short takeaway is all rows are versioned, and your row versioning can get very complex. So what you really want the database to do is to take away that pain of managing the versions. Implicitly in XTDB, we filter out all those versions by default because that makes the simplest possible user experience for a developer. The developers don't want to have to think about historical versions they no longer care about, just because someone else who needs to audit the system might care about them. We just want to be able to just select star and see currently valid versions. But if you ever need to access those old versions, they're always there. So you don't have to build in the auditability or how to analyze history into your schema in advance. You just always can feel reassured that the ability to go back in time is there when you need it. And so that's kind of the elevator pitch for XT. So we take this syntax from the SQL 2011 standard, which defines valid time and system time. Where we make it orthogonal, universal across all the tables. And then we've taken this model and applied it so that it's actually efficient to execute all the way through the stack. So we've written our own execution engine on top of object storage, which is built using Apache Arrow with a sort of custom vectorized engine on the JVM, and it's all open source. And we're very keen to see what people can do with this. So
can you walk through that select statement? The because it has the for valid all and then for system time as of. What's going on with that one?
Yeah. So this particular example, the for statements are attached to the product table. So we're essentially changing this filtering of the product table. So valid time all means show me all versions throughout valid time. So this could be like if we go back a couple of slides to this one, like it's like show me all the versions that were ever known, and then system time is the state of the database as of month end. So it should hopefully become clear. Or this model, I think it takes everyone a little while to understand exactly what this is showing, but hopefully by the end of the talk it'll be much clearer. But yeah, this specific query is show me all versions, but it could be like show me what I thought the price was on the 1st of November as of the second transaction.
Okay, I guess so. There's like the for valid time, and then there's another for statement. That's all in the same query. So you're like, it's almost like reading two tables. Is that like based on these two timestamps? Is that the way I should think about this?
I would say it's about a filter on a single table. So if I go back to this one, like there's a single table. The rows have many versions, and we are filtering. Normally, you just want to filter them to now, but you're sort of expanding the filter for that table. And these are only the base tables we're filtering. So if you have like intermediate relations, they don't have these valid time columns, but we have like these hidden valid time, system time columns throughout.
Got it. Okay. Thanks.
Okay. It should. Yeah. I just wanted to make sure. In case
Jeremy,
after the first few minutes.
Can I ask a clarifying question?
Please.
This has been a while since I've looked at Snodgrass's work, but from my high level understanding of that was the system time is like snapshot time, like snapshot isolation, the time that is recorded when things enter in the database, and the valid time was more semantically associated with what the events were. Is that the high level way to understand those two interpretations of timestamps?
I would say the phrase I have in my head is system time is the time that data was entered into the system, and valid time is the time that data was actually valid in the real world. So it's always like an upstream timestamp, because unless your system itself is generating the data, like it's like an internal state within the database, most data is modeled from reality, and reality is always upstream of the database. So valid time is like this, accounting for this delay, basically.
Yeah, and valid time comes from the user semantics, right? It's the system's not generating, right, as opposed to the system time, which is kind of what you do when you are entering the data and automatically recording timestamps for doing things like snapshots and versioning and stuff like that, right?
Absolutely, yeah.
Exactly that, yeah. So valid time you'll also hear called application time or business time or domain time. I mean, because our industry can't ever agree on a single name for these things.
Yeah, great. Thank you. Appreciate that clarification.
No, I think it's a great segue, because semantics is what it's all about, right? So we wouldn't be giving this talk if we didn't care about the semantics of the way that data mutates. Like there would be no point building a database if we didn't think that this semantic model was better. And for reasons we'll go into, you can't just take this semantics and apply it on other databases and expect it to be efficient. So just to run through the talk, then I want to sort of start with the semantics and justify why this is a good idea, and explain that the timestamp and how they work a bit. The timestamps work a bit more, and then we'll go. James will take a tour through the storage and indexing, and we'll maybe touch on the compute and storage if there's time at the end. Yeah, the motivation certainly is the semantics. So our target audience for XT is when there is a user or like an auditor involved. So this is very common in regulated industries like finance, but insurance and healthcare, where the auditor or the end user wants to be able to run reports and then rerun reports using, but correcting the data. So they want to be able to see and verify how data changes over time. And this is like the sort of key buying signal. Like if this person exists, it's like XT is in there, because basically most databases fail at allowing you to run reports and make corrections in a sort of semantically generic way, and then rerun reports with those corrections in there. The other sort of key motivator is that a lot of these problems we're talking about, they can be worked out through the schema, but doing that and sort of expanding your schema with all these other considerations and having other timestamp columns is very complicated. And as a sort of technical leader in an organization, you don't want your developers wasting precious project time on auditing requirements that could be pushed down or pushed out to a database vendor. So because it's like loads of work to do it, and there's all kinds of room for bugs, and no one wants to be responsible for that. There is a sweet spot where, because of the way XT works, we're not focused on like big OLAP systems. We're looking at where an LTP workload can fit within a single box, basically, or at least the transactional write volumes can fit within a single box, and where the costs of retention are more important than like having super low latency. Right? We're not a super low latency system. We're just worrying about how we correctly store and audit data. And then, of course, you have application developers who we also want to appeal to, and they view XT slightly differently. They will say, well, I really want things to be mutable and versioned. Like this feels like Git. It's good, and people are crying out for other aspects, which we'll talk through. I would say our target audience is growing every year, like as more and more regulations apply to new industries and existing industries. Everyone is asking for more provenance, more data integration, and more integrity of overall systems that get built. So I think the sort of compelling reason to care about the bitemporal model, finally, after almost 40 years, is making sense. I don't think back in the 80s people had the same care about auditing as they do these days. But I think it's an important moment. So those are the trends, but I think those trends map to semantics, which I'll simplify as consistent, complete, and correct. And we'll walk through exactly which parts of the bitemporal model is allude to. But consistency, we normally think about in terms of ACID. And I think in SQL, the biggest source of consistency problems is actually how we define update. So naively, an update is a delete plus an insert. This is how the original SQL spec was defined, or how SQL was originally outlined in the original papers, where hard drives are very small and you had to make sure you deleted data, otherwise you'd run out of disk. So it sort of made sense in that time, but it's 2025 and this is still the way that people use SQL, and that's a problem. So what do you do if you don't actually want to delete things and if you want to handle accretion of information? So this has been talked about many times over the years, and actually one of the motivating inputs for working on log structured merge tree techniques. Patrick O'Neill, who was working on that, read all about these update in place problems. So Jim Gray talked about it. I alludes to a paper by Ben Michael Schuler in 1977 about why update in place is bad. And everyone, throughout the 80s and 90s was thinking about this. Lots of people were thinking about this, and it motivated log structured merging as an antidote or a solution to the update in place problem. And if you take this to its logical conclusion, to build a database that is just a log structured merge tree, really get a temporal database. And a temporal database is what I think is the logical conclusion to this history of HTAP, where originally we had OLTP. Then people decided, well, that's not fast enough for certain analytics workloads, but because OLTP keeps forgetting history, OLAP remembers it. We need to use OLAP systems to query history. And then finally people are like, oh, no, we still need the transactional support so we can tie decisions together and do the auditing. And that's why we have like the HTAP world. It's like people don't need the full scale of the big OLAP systems. They don't need the extreme speeds of the OLTP. They just want one system that can handle quite a few transactions, a few gigs or terabytes of data happily and is fully auditable. And that's our sweet spot. But I think this breakdown that Andy, you presented a few weeks back of like looking at it through the lens of workload and operational complexity. Operational complexity is like quite a high level view, and I would actually break this down further and say that at the bottom of all of these divisions, or this bifurcation between OLTP and OLAP, you have the distinction between current and historical. So current data being what OLTP systems are built to care about, and because they don't care about history, like of course you need OLAP, right? Because like by definition, OLTP doesn't attempt to keep it. Now, of course, there are exceptions to that, and we'll touch on how OLTP systems have tried to incorporate history, but hopefully this gives us a framing for a root cause of the sort of semantic problem here, which is that OLTP forgetfulness is creating all kinds of issues in the wider landscape. And if only OLTP systems didn't forget and didn't only care about current data, we could be much better off. And I think it's proven by the way that people, write event-driven systems. They write events down into Kafka and then put the data into Postgres. Or on the OLAP side, a lot of people spend a lot of time duplicating schemas from the OLTP systems and then running OLAP queries, which really, they're not vast OLAP queries. They could have just been run on the OLTP system if only the OLTP system kept the data properly. So OLAP is not always the actual necessary solution. It's just, and if the scale, it's just there because people, the application guys don't want to have to write the auditing layer. And I think this temporal database gap was quite clear to Joe Hellerstein when he wrote this paper looking back at Postgres. I took a screenshot of a chat I had with another colleague back in Slack a few years back, where in the paper he talks about the notion of versioning and time travel in databases being ripe for a comeback. And actually Postgres had versioning. So everyone knows Postgres has an MVCC implementation, but originally it didn't actually garbage collect, what's the word, clean up those old rows. It would keep them. So you could go back in time and see those old versions of data. And like this would have been great, but again, back in the 80s and 90s, disks weren't big enough to make it practical. But now we're in an era of object storage. It's plausible, and so we should reconsider the semantics. And there are all kinds of other systems which touch on this temporal issue. And I think maybe the most important way of viewing it is that everyone wants real time, and real time is expensive, right? This diagram on the right here sort of shows that if you want things to be as near to real time as possible, the costs only go up. But very quickly the costs go down, and then as you move data into colder and colder storage over time, it gets more expensive to retrieve it again. And all of these other systems that aren't OLTP systems or HTAP systems, like whether it's streaming or pure warehouses or things like feature stores, they all take in data that's timestamped. It's got an original event time, and they store it, and then they have to figure out and join across the different sources to make sense of the world. Right? These are all downstream problems of the OLTP systems not keeping history. That's not to say that these other kinds of systems shouldn't exist. It's just like they exist in the context of OLTP failing to expand its own feature set. So let's take a step back and design what we think an OLTP system should look like, which is temporal. So what if it always recorded linear histories of rows, and not just single rows, but what if the history of the entire database was linear? And then we could integrate the histories of not just rows or records that exist within our database, but maybe we get some from other databases, right? We want to be able to pull the information from many sources and integrate those histories. And then we want to be able to run meaningful auditing queries on top of those many histories that we store in our database. And so these three layers, again, consistent, complete, and correct, I think build a picture of what's needed, which is the bitemporal model. Just to go through in order, though, so consistency, we start with the epochal time model, which is something James and I took a lot of inspiration from Rich Hickey, who is the author of Closure, Lisp programming language. And he, in this talk, very clearly outlined what he considered a very powerful model of time, which is taking immutable values and then having processes which transform those values in a deterministic or a very regular way, so that the semantics of observers aren't impeded. So everyone can observe many states independently without having to wait or lock for each other, right? This is it's not even talking about software. This is more like a model of how reality works. Multiple observers can observe the same thing without preventing that thing from changing. Whereas all of the systems traditionally that are place-oriented aren't built around this model. And so they all suffer from very complex software implementations. So Rich took this idea and applied it to Datomic, which is not XTDB, but it was directly inspired XTDB. If it wasn't for Datomic, XT wouldn't exist. But Datomic took these views of how to think about immutable successions of time and applied it in a global way to this database, which had some real success. Like it got acquired by Nubank, but the fundamental model is the same as what, say, HStore or VaultDB we're looking along the lines of, which is if you have deterministic transactions, then that are read, they're non-interactive, so you can't do interactive reads during a transaction. It's like a simpler way of thinking about the progression of state, but it's also potentially much more efficient to execute. Right, the speed of a single core is very fast, and many OLTP workloads can fit in that linear serialized execution order. But crucially, it means everything is immutable, and you have this snapshot consistency. So this is like the basis of our consistency for XTDB. And this is how we reify it. So we actually use Kafka. We use a single partition Kafka topic, and we put all of our transaction payload onto the topic, and that becomes the write-ahead log effectively. And obviously the partition determines the serialization order, and then the nodes, and there may be many nodes in XT, the nodes race to index that deterministically and do compaction into the object store. So we take data that's put into Kafka, pop it into object store. So it's a very stateless system, very minimal coordination. The nodes never need to talk to each other because they can all agree on the state of the database at any point in time.
Go back to architecture just to understand. So it's the PostgreSquire protocol. I call begin. I can read some data that hits up whatever the current NGPs, and then when I do my updates, you apply the changes to, you just buffer the changes in the right set for the transaction. They call commit, and then that gets shoved to Kafka, who then goes ahead and applies it. And then presumably, I mean, maybe James can talk about this, but you have to then coordinate the transactions in the front. And so you're doing that. You said you're doing that deterministically, or how are you guys handling that?
Yeah, so the transactions themselves are entirely sort of non-interactive, as Jeremy says. So what happens here is if you do make reads beforehand, we then offer an assert primitive, which then is optimistic concurrency, essentially. It then checks when this transaction gets indexed, it checks all your preconditions.
Got it. Yep, got it. All right. So DynamoDB, reconnaissance transactions, and Calvin. Got it. Yes.
Yep.
Exactly. Yeah. It's a very simple model, and we don't do anything clever to accelerate it at the moment, at least. And there probably are some more tricks we could apply, but it's like do the dumb thing, and it's literally serialized. And Datomic implemented this model, and I don't know if you saw the Jepson report on that, but AFA couldn't find any flaws in that. Right, it was perfect. He didn't manage to find any bugs. So I think it's a testament to simplicity.
Can you share what? I know what a typical OLTP transaction might look like in web applications and other things. What do transactions look like in this world? Is it read, modify, write, or bulk inserts, or are typical transactions inserting 20 things at a time or one thing at a time?
It could be large. Yeah, okay. The actual limitation, the hard limitation, is on the Kafka write-ahead log. So Kafka's default measure size is 1 megabyte. So right now we say chunk up your transaction so it fits in a megabyte. Otherwise, you have to use a larger configuration.
Okay.
But there are some caveats to this model, right? So if you have an update statement that actually does a huge change to the database, it might be a very small statement, but the actual effect might take a long time to apply. You're going to be stalling other writers. So you want to avoid those sorts of situations where you're stalling the progress of the transaction queue.
But then is the write-ahead log, are you logging a logical level, here's the queries I ran, or is it the physical changes?
It's logical.
Got it. Okay. All right.
But,
so, yeah.
but they're more like requests for transactions, right, at this point. So that it's not like these are the transactions which have already been applied, then they go on the write-ahead log.
Yes, got it. Thanks.
Yeah. It's a very easy model for us to put all of the the ACID work onto the object store and the Kafka. We don't do any distributed systems, clever algorithms. We don't have to do any of that. We don't have to worry about any of the durability. It's all outsourced, which has its cost, right? There's some latency introduced by using Kafka, but for our purposes, it's good. Cool. So I'll proceed. So the next sort of problem is that, you end up with multiple sources. So how do you integrate multiple databases? How do you do that in a consistent manner? So in order to answer a question like, were we profitable last week? You need some way to align that. So this is like very simply modeled as like an extra timestamp on on your data as you ingest it. But what is actually the hard problem is corrections, right? Because your relevant data set, the data in the database, and noise all exist in the same world, and you need to separate these things and make sure that your query can be satisfied with what's in the database. And these circles, they may change over time. In the ideal case, you end up with all of your data that you ever need in the database and no errors. But everyone knows that's you never get things right first time. Things evolve and move. And actually, this was part of Ben Michael Schuler's 1977 paper, where he basically outlines that entry lag, obsolescence, and errors, if you model these things as first-class aspects of your database, you sort of sidestep a whole load of problems to do with how do you manage things over time. So he argues that this is like really important. And this is before the bitemporal model was coined. And I think the bitemporal model essentially implements this. And he would be very disappointed with the current bifurcation, where we sort of say, oh, OLTP just cares about this part of the Venn diagram, and OLAP covers everything, but it doesn't really understand the semantics of how these sets move and shift around, because we don't have ways of talking about errors and obsolescence in SQL. So as a consequence, we in common OLTP world, when people build applications, instead of doing updates, they'll say, no, just insert a new row and we'll roll up the versions, or insert into a history table. Instead of delete, you just update a previous row. And this means everyone is having to filter for timestamps, making sure they're only seeing like the latest version, or they're moving everything to OLAP systems. There are ways of getting history to be modeled in OLTP systems, right? You can use audit tables and soft deletes, and you can model your own like bitemporal kind of columns, like slowly changing dimensions is a common pattern. You can denormalize things, like if you store the price of a product at a point in time at the point of checkout, like, okay, that kind of works, but then you denormalize the data to record that price as it was at that point. Is that a good idea? Could be. But if all else fails, the answer is always go back to the backups, replay from write-ahead logs, or rely on your change data capture. So like there's no good answer in most OLTP systems. It's a huge source of bugs to try and mitigate the fact that OLTP doesn't retain data. So the bitemporal model.
So the SCD stuff, that's like the Kimball data warehouse stuff in the 90s, like the type 1, type 2 thing?
Yeah, it's just a different way of sort of describing how data should change or can change, or how you represent that. It's a modeling thing, but people can apply it to solve the problem of data retention in transactional systems as well.
And it's slow changing data, SCD, or dimension, or one of the two?
Slowly changing dimension is normally the application. Yep.
All right, thanks.
Yeah, so I'll just run through. So the bitemporal model is defined in SQL 2011. So there was a paper that was written sort of looking at that, and they have these definitions as the time when something is committed to the database, and then the time when something is regarded as true by the user, which is, it's a user semantic. So if we look at a concrete example now, we may want to set the price of this IDA to 4, so we can run an update statement, and now our table has 2 entries. So this is just system time, and you notice that we close the period for system 2 gets closed, and then in the first row to T3, and then we insert a new row that starts at T3 and goes to infinity. And the semantics of that, it's closed open periods. You're not allowed overlaps. The system should maintain this. Like, the user shouldn't really think about editing system time. It's there when you want to view it, but you just do an update and it appends into the table. Valid time is, of course, different, right? You're able to backdate and say, the price, I want to show that the price from the 1st of November was 5. So you can do that. You can enter the information to the table and say it was valid from 1st of November, valid to infinity. But then if you make a mistake and you realize, there was a data entry bug, or some process or batch job went wrong, a program failed, it should have been 4. And you can represent that in the valid time view of world by saying it's valid from the 1st of November to infinity. And then if you then want to set it to 3 as another operation, so 3 operations here, this is how the table would look. So we say it's valid from the 1st of November to T3, and then from T3 to infinity, the price is 3. So this is a slightly more simple example in a sense. In it doesn't have any other data. It's just one item in one column. One item in one table, but apply this to all tables and many items, and you understand that there's a lot of potential complexity in the way versions are managed and indexed. And so that now you combine both the valid time and system time dimensions, and what we're seeing is like a proliferation of rows. Again, like no overlaps. You're only appending the only time you ever update any existing rows to say the system 2 is closed. And then the other interesting thing here is that in the bottom table, we end up with an extra row. So we're doing these 3 operations like that we did in the previous slide, but we have 4 rows instead of 3. And this is because you actually have to split rectangles. And this will become clear in James's discussion as to why you need that. But basically, the implementation for this isn't easy. And actually, if you try and do this with like TPCH data, you end up with like all these join conditions for all the tables. Like if you assume all tables are bitemporal and you want to do an as of now query 5, like the query gets really complicated, and you have to have a trigger on all of those tables. So this is just like one trigger for one table, which updates and maintains these rows. So when you do an update, it has to insert and close the period, etc. So it's quite a hairy thing to implement yourself, which is why we think there's scope to do a good job at it. The bitemporal model, as per SQL 2011, was standardized. Some databases tried to implement it. I think it's got a lot of problems. It's very complex to use. The way it defines application time or valid time is ambiguous. Doesn't address schema migration. Schema is a huge part of this. Like when you migrate the schema, do you migrate the history? Does that break everyone's as of queries? Like these are big unanswered questions. And it's too vague because I think valid time should be universal, or we think valid time should be universal. But various databases have implemented it per the spec. So Teradata, DB2, HANA, MariaDB, and a few others have all, they have documentation that talks about this, but the reality is no one uses it, or like it's barely used by most users because it's bolted on. It has a performance impact, which has to be measured and assessed. And the UX is just very complex. So like it's not like on by default, and certainly Postgres doesn't have it. I will just mention briefly time series databases, which are sort of related to this as of snapshotting problem, but they're not the same. So time series databases are focused on events rather than states, which states have durations. The thing they give you is the ability to do like an as of join, which is it's about lining up different events across tables, but it's something you do at query time. It's not about how you maintain state in the database. It's not a model of reality. It's like assuming you already have some flat event data. But time series databases do accelerate workloads that have needs for very advanced windowing functions and roll-up aggregations, etc. So we're not doing that. But as of join is sort of evidence that people need these temporal query abilities, right? Snapshots aren't enough. They need as of joins. And XT kind of solves this problem in a different way. It says if you load your data into the database using valid time, then it works. So XT is bitemporal by default. We think this is a much better standard of way to think about time. If developers, if application developers don't have to think about it until they come to like an auditing requirement, people will actually use it. So when you do an insert, it's just an insert. An update is just an update. Delete is a delete because it hides the data. If you actually want to delete the data, there's an erase operation. All queries are as of now by default. And because it's like an HTAP system, we service transactions and we service analytics. It means that there's no need for ETL, right? You can still do ETL, but there shouldn't be much need unless you have some extreme performance requirements. And yeah, with that, I wanted to sort of say that the other way of framing this, as James has put it on many occasions, is that any sufficiently complicated data system contains an ad hoc, informally specified, bug-ridden, and slow implementation of half of a bitemporal database. And for that reason, you should just use a bitemporal database by default if you end up in that position. So with that, I'll hand over to James to whiz you through the storage layer.
Thank you, Jeremy. Yes, and for those of you who do know where this one came from, it's Greenspun's 10th rule. And there is an oft-quoted corollary to this, which is including common Lisp. And I'll let you decide whether that corollary also applies to XTDB as well as we go through. But yeah, so Jeremy's right here. I mean, what XTDB has come out of is all like in previous lives before working on XT. It's come out of us implementing exactly these systems, right? Ad hoc, informally specified, bug-ridden bitemporal databases. And it was time, by the time that we all got together to make XT. It was time to make it and do it once and for all. Have it baked into the database from day one. So what we did, one of the first things we did was that we looked at the shapes of bitemporal data. Like what does temporal data actually look like in practice? Like what are the data sets that we're working with day in, day out that cause us the pain that we're trying to avoid by using a database like XT? I've got a big warning at the top here. As I say, there's going to be some sweeping and generalizations in the upcoming slides. So the assumptions that we're making is that the vast majority of data is inserted where valid time is the same as system time. This is what's happening sort of day in, day out. It's rare that or at least relatively rare, that you're going to be doing either retroactive or scheduled future updates. So there's a few dimensions that I want to consider as we run through these, as we run through this taxonomy. So number one is the cardinality. So how many distinct entities do we have in this given data set? How many updates do we have for each given entity? And what's the sort of bitemporal characteristics of these data sets like? So when we put a version in, what does that validity period look like? And then finally, how do we actually end up querying these in practice? So there's a couple of different query patterns that we're looking at, and these are no stranger to anyone who's worked with databases. Like they're relatively there's nothing sort of different about XT in this regard. Like we're looking at filtering by primary key. We might be filtering by it's like a near unique key, like an email. We might be looking at what we call a selective attribute. So an individual store of a US chain. And I did actually look it up, and apparently Walmart has 5,000. Or about 5,000 in the States. For some reason, as a Brit, I thought that was a lot more, but no, 5,000. And we've got unselective attributes, and then finally we've got full table scans. On the temporal selectivity side, though, this is where sort of XT does diverge a little bit here, because there's very much an order of priority here. If we look at the sorts of queries that people run every day on their databases, we would say the vast majority of this number one here, where we query for both valid time and system time as of now. It's a rare requirement that, for example, we need to see the whole history of an entity. And it's an even rarer one that we need to see the history of the entity as it was at a previous time. So in order of priority, valid time, system time as of now, valid time history, and then system time history. So there's an asymmetry here to the two temporal dimensions, which if you read the papers, like a lot of the papers don't mention this asymmetry, but this is one that has come out of working with temporal data in practice.
Sorry, what do you mean? What do you mean by the priority in terms of actually, like what the application wants, or how you're running the query and just determining whether something's valid to be shown right now?
We're talking about what end users care about, and hence what we care about in terms of optimizing. So if we're going to make trade-offs, then we're going to trade off having a slower system time history than we are valid time.
Got it. Thanks.
So if we look at some sort of shapes of bitemporal data, and one category here, the first category is like product pricing or user profiles or employee records. And here we're looking at quite a slow growing cardinality, relatively speaking. So like your cardinalities of products, like how many products you're going to have in your catalog, is never truly massive. Similarly, sort of user profiles or employee records, not at least relative to the ones I'm about to cover, at least. When we look at updates to these things, the vast majority of these updates are for valid time from now until corrected. So when I'm updating my product price, I'm going to say I want this change to take effect immediately, and I want it to take effect until I then correct it later. So we do have some retroactive and scheduled updates. So things like, user profiles is a good one for this, because you'll get like an HR system where someone will tell you that they moved house last week or they're moving house next week. But I say they're relatively fewer and further between. If we compare that, though, to sort of trade or order data or social media posts and messages, these have a massive and very fast-growing cardinality. So we're getting new trades in all the time. We're getting new social media posts in all the time. And these form a state machine. So what tends to happen here is that your updates to these are very much, say, biased towards recently inserted entries. So if I'm Twitter or whatever it's called these days, I might allow an edit window of 15 minutes or whatever it happens to be. But until a certain point, people are going to stop editing their posts, in theory. So the valid time is still now until corrected, but when they hit a final state, and they tend to hit a final state quite quickly, relative again to sort of the products or the user profiles. When they hit that final state, they then remain valid indefinitely. So category 3 is IoT readings or pricing feed data. So I'm differentiating here between sort of product pricing, which if you've got a product catalog, versus pricing feed data, which is like if you've got a market data feed, you've got stock tickers coming in however often they update. So here we've got a relatively low cardinality. So we don't have a great deal of, like, let's say we don't have a great deal of sensors, for example, if we've got a sensor network. Relatively speaking, we don't have a great number of those. But the difference here is that the update frequency is very high. So like one of the clients we're doing some work for at the moment here. So they're getting sensor readings in every 5 minutes for each sensor, and they've got a decent network in, probably into the tens, hundreds of thousands of sensors. So the update frequency is what dominates here. And what we recommend here is that each version is entered with a very short and bounded valid time period. And sometimes, if it's an event, this may well even be one chronon, as Rick Snodgrass and Christian Jensen call it, so that the smallest indivisible unit of time that the system can handle. And finally, and I've left the boring one for last, it's the static reference data. So this is your data that's got sort of relatively low and static cardinality. It's not updated all that often. It's relatively frequently accessed, and it's small, so it's likely to be completely in cache. So again, not one we had to consider massively, but one in here for completeness. So one of the big things that we have to do is we need to calculate what's visible at any time. So what of the data that we store, what is it, like which rows, which versions are visible to the query in question? And we, as Jeremy says here, we extend SQL 2011 here with two extra clauses that form part of the from clause, or for a base table. So we've got for system time and we've got for valid time here. And again, there's a few different filters that you can specify here. But crucially here, XT defaults to for system time as of now, which is the SQL standard, but also for valid time as of now. And the impact of this is that XT behaves like Postgres for the vast majority of the time. Until you actually need the bitemporality, you can treat it exactly like Postgres with its inserts, its updates, and its deletes. But when you need that history, it's there and available. So what do? Well, we store immutable bitemporal events. And these consist of a system from, a valid from, and a valid to. So note here, no system. We don't actually store the system to in these events. So here I've got 3 updates. Again, that's keeping a similar examples to Jeremy's from earlier. And you'll notice here in the third update, the one at system time T4. This is one where we're doing an update back in valid time. We're saying that there was a version that we need to sneak in there in between version 1 and version 2. So if you don't have a bitemporal database, what happens? So first time round, I'm going to be putting in a version from T1 up until infinity. As Jeremy mentioned in his introduction earlier on, we then, when we get this update through, we then have to take control of remembering exactly what to update, both on the system time and on the valid time. So you'll see the new row here in green, but in inserting that new row, I, the end user, then have to remember to make the changes here that are outlined in orange. And the third one is even more fun, because what I'm ending up doing by entering this red segment in here, I'm actually making changes to 4 rows there out of the 6. And I'm sure you'll believe me when I say it took me an embarrassingly long time to get this right, even though I've been working with temporal databases for however long it's been now. Right, this is error prone, it's fiddly. So keeping that whole bitemporal state materialized is actually quite expensive as well. Like you'll see here, if you did need to keep that materialized, you've already got a write amplification of 2x there. So we've got 3 core events, we've got 3 core row versions. But if I'm storing it in a bitemporal way, I've got to store 6 rows. As it says here, like most common queries don't even care about the full bitemporal state. So what we do is we are inherently lazy about what we store. And the innovation here that comes with XT is that we play it backwards. So we write novelty to an append-only event log, and so those events there, you get the system from, valid from, and valid to, and the version of the documents. And when we query, we just play the events in reverse system time order, and this actually yields a number of interesting properties. So number one is that if you've got an as of now query, which if you recall is what we said was the most common type of query, we terminate as soon as we see the relevant event. Like we don't need to look events earlier in system time because they cannot possibly supersede later events for that valid time period. If we do go back in time, we can skip over later events, so events that are later in system time, because they can't possibly affect earlier than their system from. Like the system from of the query is like a watermark; it's an upper bound. You cannot possibly see anything later than that point if you choose that as your snapshot time. And finally, queries that don't project any temporal columns out, they only need to ascertain whether each event is visible or not. So we don't have to do the full bitemporal materialization in that case either. So doing all of that work ahead of time that we talked about just now, like figuring out all of those updates, is actually largely unnecessary for the vast majority of queries. So we'll take an example here. So if I keep both valid time and system time implicit, so here we're looking at valid time and system time as of T5. I play backwards through my events. I just realized you can't see my cursor because I'm controlling Jeremy's presentation rather than anything, but we'll play back through these events here. The T4 one we ignore because the valid time here doesn't apply to our query, so we can very quickly ignore that one. We then spot an event for T3. This event has valid time from T3 to infinity. We spot this matches our query. It's an as of query, and so we can immediately stop processing for this entity. We don't have to go back through this entity at all. So we can ignore any history that happened before that green line on the right-hand side there. If we do pick the valid time as of T3, the story is similar. So in this case, we see that the valid time range of the first event that we're scanning is T2 to T4. This event matches, so we yield that one to our query engine and we stop processing any further events.
Maybe you're going to get into this, but like your query optimizer has to be obviously aware of these notion of system time, valid time, and then it has to make decisions on whether, because you have to presumably have indexes to speed this up. And then is it going to decide in some cases based on what the semantics are of like the bitemporal portion of the lookup, like whether it's better to go to like the ID index first versus the timestamp index, or does it always make sense to go? Well, I mean, if you have the ID index, that's the primary key. But if you don't have that, then you could decide which one of those two you have to look up on.
You do, yes. If it's all right, I've got some slides a bit later on that I can cover.
Yes. Okay. Perfect. Thanks.
So what we do when we play it backwards, if we do need that full materialization, you'll see we start the graph from the other end. So we create this row first of all. We then have this concept called a ceiling. And what the ceiling says is what's the portion of time that I haven't yet covered with an event. So in this case here, for my valid time prior to 2, my ceiling is infinite. Like there's no events there that cover this. There's no events that cover this period of time. Between valid time T2 and T4, I've got my ceiling as provided by the red event here. So the red event here is providing a system time ceiling of T4. And then similarly from T4 to the end of time, there's no ceiling yet for this. So when we get our orange event in, we then use that ceiling to create our rows. So what we're doing is we're applying the orange event, but we're applying it underneath the red one. If you think about it in terms of like a Z order type thing. And so when I construct my rows, I can add 2 rows on here. because I'm constructing one row for the segment from T3 to T4 and one row for the segment from T4 up to positive infinity. We then update our ceiling as we go. So here we've now got a little step in our ceiling. It comes down to T3 as a result of the orange event. And then when my final event comes through, I've now got three distinct segments to think about. I've got the segment from T1 to T2. I've got the segment from T2 to T3, and I've got the segment above T3. And so I add 3 rows in here at the bottom to cope with those 3 rectangles. So the biggest note here is that at no point in this process have we updated or even looked at any rows from previous events. Like we're not talking about sort of any kind of sort of updating in place of those. We've managed to, and because we don't have to read them either, we can yield those rows immediately as to the downstream query engine as soon as we've calculated them. So I said earlier on, just play the events in reverse order. Easier said than done. Because we obviously don't want to play all the events for every query, and we obviously don't want to maintain a fully partitioned sorted data structure on every update. That would be crazy. So what we do is we've got a distributed log structured merge tree, or LSM tree. And this works pretty much the same as all of the other LSM literature, so I won't go into it too much here. But the main thing here to consider is that all of these files are immutable. So they're very amenable for storing in a remote object store and also for caching. Our second innovation here is a concept called recency. And we define recency for record, as it says here, as the maximum timestamp for which the row was believed valid for both valid time equals t and system time equals t. Why do we do this? Let's have a look at what it means. So you'll see here a bitemporal polygon, which will come up from one of those, which will be the result of one of those events that we saw earlier on. So we first of all take the vt equals st line. Our recency is then the point at which this vt equals st line leaves the polygon here. But what this means is that any query that's upwards and to the right of that recency has no reason to look at this event. Right? It cannot possibly affect this query, which means that when I'm looking for queries as of now, I can filter out any events that have a recency less than now, which turns out to be your whole historical partition. So this also applies on a file-by-file basis as well. So recency being a heuristic, what I can do is I can say that the recency for a file is the maximum recency of all of the events within it. And therefore, I can rule out entire files based on the recency of the query that I'm looking at. Another observation, the Lindy effect. So this helps us out with our storage as well. And the Lindy effect comes completely from outside of tech, as far as I'm aware. It was originally to talk about businesses. But the Lindy effect states that the future life expectancy of non-perishable things is proportional to the current age. So I think originally it was referencing businesses, but books, it's true for books as well. And music, particularly as my father keeps reminding me that they don't make music like they used to. But more closer to home, this is very much the inspiration behind generational garbage collection. So what generational GC says is that when you've got like very recently allocated objects, chances are they're going to be used for a short period of time and then discarded. So what they will do is they will very much prioritize collection of the most recently allocated objects. Objects that have survived then a few of these garbage collections are then collected much less frequently. So you get your old or your survivor gen, whatever they may be called. Most importantly to us, the same is true of data systems. So if you think back to that taxonomy from earlier, when you do have newer data, it's much more likely to be very quickly superseded than data that's remained true for a while. So if you think about like the trades or the social media posts that have been created a long time ago, chances are they're not going to get any further updates now. And we use this as the basis of our LSM compaction. So what we do in our LSM compaction is we, first of all, when our in-memory buffer is full, we flush out level 0 files. So that's a standard LSM tree pattern. We then apply our compaction process to it. And the compaction process out of these L0 files splits us up by recency. So if we have a recency that's indefinite, it stays in a current file. If a recency isn't indefinite, so if it's already historical, if it's already been superseded, it moves into a historical partition, which is separate in the LSM tree. We then, as we get more L0s in, we compact them up. So we'll take one current file and a few more L0s, and we'll create some more historical and current files out of that. As we go up the tree, we then start to partition, like when we get these, when we fill up these L1 files, we then introduce some partitioning on the current side by the ID hash prefix. And what this does, to Andy's question from earlier, when we got questions, when we got queries around like searching for primary key, this very quickly filters out entire files of events that we don't need to look for this particular query. We do then do sort of standard practices here around Bloom filtering and metadata as well, and those cover the they generally cover the selective and the near unique pretty well as well. So one of the things that we notice is that in practice, again thanks to this Lindy effect, one of two things happens, exactly one of two things. So either the historical side of the LSM grows really wide because data, as soon as it comes in, becomes historical. So if you think about reading when it comes in, it's very quick, a sensor reading, it's very quickly superseded by the next one. And similarly for sort of market pricing feeds. So we see in those cases the historical side grow very wide, or the current side grows deep. So then this is looking at the trades or the user profiles. So what's happening here is that when a trade gets completed and essentially closed, at that point it gets deeper and deeper into the current side of the tree as it gets older and older. And then we can look at these older parts of the current tree and very quickly filter them out based on the temporal metadata on each file. So coming back to the shapes of bitemporal queries, and you'll see we've covered these off through the various observations that we've made here. So the primary key is covered by the ID hash filtering on the LSM tree as it gets into the deeper levels. The files themselves are also then partitioned by ID, so we can quickly narrow them down to pages within the file as well. Unique and near unique keys, metadata and Bloom filters make a great job of these. They very quickly identify the files where this particular email is present. We are shortly as well going to be adding secondary indices to XT, so these will turn sort of emails into entity IDs quite quickly. Selective attributes, less so. We get quite a lot of sort of Bloom filter false positives by the time it gets to this point. And then selective and unselective attributes and scans tend to just be scans anyway. And because XT is an arrow database, it's the columnar side of this is quite fast. And again, looking at the temporal selectivity here, we very much prioritize, as I say, for the first one here. So because of the way that the historical events are very quickly filtered out, we can, I say, hone in on the current time events. I say all of this though has come out from the sort of the practical experience that we've had both working on temporal systems before XT, but also in conjunction with our design partners. So I'll hand it back to Jeremy to talk about that.
Yeah, thanks, James. I think it's fair to say that we actually spoke to Richard Snodgrass early in the year, and like when people approach the design space, they don't like all the other database engines that have implemented bitemporality. Like no one's gone to the levels we've done to push it all the way into all the scans, right to the bottom of all the storage that happens. But yeah, this design has been proven out with our design partners. So we have this energy infrastructure reporting company, which is you've got a very large installation of like solar panels, etc. There are lots of sensor readings flooding in, and they want auditability so they can report to their regulator, like this is what the power levels were, what we thought the power levels were, and after some delays, how they get corrected. But yeah, I just want to finish really quickly with some implications of what those semantics actually mean in the SQL. We've seen some snippets of SQL. The big one is SQL 2011, but we've taken this and extended it a bit. We've added lots of Allen period operators, which SQL doesn't normally have. It means you don't have to do lots of less than and greater thans. It's like very simple predicates. You can say I want to run this query between these two dates, do these sort of sequence valid time queries. Everything is sort of a record by default. Like this is a whole other, could be a whole other talk, like how we manage schema. But by default, everything is kind of schemaless, but it has certain advantages. And we are very good at storing very deeply nested data. We can also support blind writes. So because of the event model or the way writes are written in, we can say, well, if you know the valid from, the valid to, we can efficiently store that. And then it travels through the ingestion pipeline very quickly. So again, very good for sort of sensor readings, that kind of thing. We reify the transactions. So when you need that auditability of exactly what the transaction timestamp was, like it's there, it doesn't get garbage collected when the LSN cycles over or anything like that. It's like it's first class audit log. We have the ability to query across multiple databases. So you could potentially have like products in one database, prices in another database. We've mentioned PostgreSQL compatibility. It's actually been quite a boon for us. It's allowed us to support Metabase, which has been very key with our design partner. Also 11 languages. I've been able to test all these different drivers, and they actually work quite well with XT, getting data in and out. We just added Arrow as a custom OID to send Arrow data backwards and forwards over Postgres. And it fits well with the transaction semantics. So just because you can't do interactive transactions, it actually feels okay at the pre-SQL console. We have actually implemented Flight SQL, and we've been hacking on ADBC as well. So that's landing and actually works quite well for transactional data sets. I was surprised by the performance numbers we've seen. But yeah, certainly very good for large result sets. And we have had a couple of side quests as we couldn't resist hacking on things that aren't just the bitemporal aspects. One is the SQL language. We want to make it more template friendly. We know one of the big pains that people have with SQL is that it's hard to write applications against. So we have this extension to the grammar. It allows many commas, and we also have like a pipelining operator, but it's not implemented as syntax. It's just a sort of a flexing of the grammar. That means we have relational closure, so you can chain operators and compose SQL in a kind of interesting way. There's a whole blog post on that. We also have our own query language, which I'm not going to touch in any depth, other than it's a Lispy SQL, but you can embed it in your SQL if you want to experiment. It's definitely unstable for the moment, so we do recommend people use the SQL if they're building in anything for prod. So that's the recap. Yeah, we haven't talked about Kotlin or Clojure or how the vectorizing execution works, but hopefully it's given you a taste of what XT is and can do. People are often going to say questions, how does this compare to Postgres? I have just recently put this to do MVCC site. If you know to do MVC, the idea is to can we make a database thing out of this? Right now it's like XT versus Postgres. And I haven't actually fleshed it out. So watch this space. If anyone wants to collaborate on this, I'll be really interested, basically showing how versioning and consistency semantics works across databases with a simple to-do example. So that is the end of the talk. Appreciate we're way over time. But happy to take any questions if there are any. Thank you.
All right. I applaud back to everyone else. Thank you, James and Jeremy. This is some heavy stuff. Open up to the audience for questions. We have time for maybe one. Then I will take the time. So the data structure and the indexes, you guys have a B plus tree, or what are you doing to look up into the log? Are you relying on the log structure merge tree to do all the filtering for those kind of things?
Yeah, so it's a couple of different levels. So the first one is the log structure merge tree, and so that gets rid of entire files,
Yep.
and within that, pages within those files. When you get down to the pages within, when you get down to the actual page level, it's then a hash array mapped trie down at the bottom. So what we do is we hash the entity ID, and then that allows us to scan through the files or search through them for the relevant attributes. By the time you get down to there, it's in a lot of cases it's actually quicker to scan through those files. The pages themselves are about 1,000 rows a piece. And Arrow makes that kind of thing lightning fast.
Got it. And then your query optimizer, is that it sounds like you're not using any bits and pieces from Postgres. So like your query optimizer is written from scratch, and then
Yes. Yeah.
is it cost based? And if yes, how are you doing? I mean, you have to support joins, right? You can do joins in XTDB, right?
Yes, I mean everything above the scan operator is pretty much your traditional database, which is why we've not really covered it, to be honest. It's the scan operator that makes XT. But yeah, above that, we have got a bit more work to do on the cost based optimizer. Let's say we've got an algorithm in there that works well enough for now. But certainly over the next few, I mean, that's as you know, right? That's a sort of database query optimizing is an indefinite job. So yeah, we're very much focused on getting this GA out the door in June.
Okay.
With a query engine optimizer that's good enough for now. I say, and plenty of optimization there to come.
Yeah, we use Simply Squared for the cardinality reordering.